Hi, my name is Cassie Plemmons, and I'm going to be presenting on my topic, which is bending the rules, visualizing the path of light around black holes. So to start off with, I'm going to give a brief introduction of what black holes are. So black holes are objects in space with so much matter that light cannot escape from it, and it's basically kind of like a vacuum cleaner and gets sucked into it because there's so much gravity and there's so much force that is being brought on it that it cannot get out. So there's different types of black holes, and they deal with different aspects, such as rotation, mass, charge. But the one thing that every black hole has is an event horizon, and the event horizon is basically just where the black hole kind of starts. It's kind of like the outside of the black hole. Um, the best way to describe it is probably just saying it's like kind of like if you think of a sphere, kind of like down in the picture below of it being the black hole, it's kind of like the surface of it. So that's kind of what that is. And um, so we don't really know all the reasons why there are black holes, but we do know for one, that one of the main or like one of the most well-known causes of black holes like forming is stars dying and then collapsing in on themselves, and it creates this um, just kind of effect. It's based on the theory of the conservation of energy, which says energy cannot be created or destroyed. So when the star basically like destroys itself, it's not totally disappearing and just going out. Since it's coming in, it kind of just creates this little black hole. Since the energy is not going out, it's kind of just staying in, and that's how that black hole is created. So what I basically just want to do through my like simulation that I've made is see how light travels around it. So the first thing that I started off with was looking at special and general relativity and seeing how uh, it works with space and space time. So special relativity is used in non-curved space, so it's flat, and the gravity is how much the space is affecting space time and like curving it. So the equation delta tau times delta t, and delta t, or the t, x, and y in this equation, and the z are the dimensions of space, like x, y, z is space, and then t is the time. So uh, it can also be written in like language saying that the interval squared equals the time separation squared minus the space separation squared. It's just saying that the time is equal to the time separation between the object and the observer, and the physical space separation between the object and the observer. So yeah. And now we move on to metrics and geodesics. So first off, the metrics are used to calculate the distances between points and how they change just based on like space and time separation. So it varies. There's different kinds of metrics and stuff, but the one that I used for this project was the Schwarzschild metric, and that long equation is the Schwarzschild metric. So it's delta tau squared equals negative parentheses 1 minus 2 gm over rc squared delta t squared plus 1 minus 2 gm over rc squared, and then the rest of that you get the basics. But just for like clarification, the g is the gravitational like constant, the m is the mass, the r is the radius, and the c is just the speed of light, and then the t is time, and tau is just that interval basically. So, and then geodesics is the trajectory of a vector to show how an object will move. It comes from the changing of the grid that the object is on and how the coordinates will vary as time continues on, and just shows like how much it changes pretty much. So, like if something's like nonlinear, it's kind of works best with that and shows that. So the geodesic equations, they come from the first and second fundamental forms. And these forms, or the first one is the arc length of a surface, and the second form is the how that arc length changes on the surface. So next we have Christoffel symbols, and they represent how the grid changes in each direction. So like we have an equation for time, we have an equation for the radius, and then we have an equation for theta and phi. So we also use spherical coordinates, and these are best used in space-time. So like we have this grid X, Y, Z, and then the theta is like from X to Y, that angle, and then the phi is like how much it is from like Y to Z or X to Z, and however you write it, whichever way you write it. So yeah, and those just say how they change, and use the geodesics equations to calculate the Christoffel symbols. So, um, yeah, and so that's the first derivative, and you also need the second derivative. So there's those equations because it has time, r, theta, phi, and it has all those equations for the second derivative, and we'll be using that for Euler's method. So for the first order and the second order of Euler's method, it's basically just an equation to help approximate what the next step would be. Like if you were taking like really, really small steps and you were trying to see what the next one would be, or were approximating what it'd be, then it would look like this, and then it just keeps going. The little graph and that's there, it kind of shows how much, or it shows like what you mean by like if you're going to the next one, what it approximately is, and then the next, and then the next, and just keep going. And you use the approximations of the like last one that you did to get to the next one. So like it's just an ongoing process, and you keep doing that over and over and over again. So yeah. And the picture is a screenshot that I took of my actual black hole simulation. You can go online to that link that's there and look at it. You can also, I've downloaded it on the Oculus, so where you can use it in virtual reality and play with it in there, which is really cool. I think it's more fun to do it that way than online, but it's still pretty cool online. I have a little QR code that you can scan, but it doesn't work well on your phone. But I just put it there just so it would be easily accessible if you wanted to bookmark it and come back to it later on your computer or something. So yeah. So that's basically how I figured out how light travels around a black hole, and it kind of makes a little swoosh. So yeah, thank you.